Now we will see bending stresses in beams. So bending stresses in beams is also known as flexural stresses in beams. So this type of stress is caused by the bending moment. Okay. So first of all, we find sigma, that is the bending stress, using the equation for pure bending. So M by I is equal to sigma by is equal to E by R. So M is the bending moment, I is the moment of inertia about the neutral axis, area moment of inertia, sigma is the bending stress, by is the distance of the fiber from the neutral axis. So if at any point from the neutral axis, at any distance from the neutral axis, you want to find the bending stress, so you can find the bending stress at that point using this equation, because by will give the distance of the fiber from the neutral axis. So sigma can be found at that distance by. Okay. Now E is the Young's modulus or modulus of elasticity, and R is the radius of curvature. Okay, the radius of curvature that the beam has bent into. Okay, so M is the bending moment, I is the area moment of inertia, sigma is the bending stress, by is the distance of the fiber from the neutral axis, E is the Young's modulus, and R is the radius of curvature. Now sigma T is the tensile stress, because if, as seen in this figure, the force is acting, so in the upper portion tensile stress will be generated, while in the bottom portion compressive stresses will be generated. So sigma T is the tensile stress generated is equal to M by I into by T, means distance of the portion from the neutral axis in which the tension is happening. Okay. Similarly, sigma C is the compressive stress generated is equal to M by I into by C. By C is the distance from the neutral axis to the point at which you are computing the compressive stress. So this is sigma C and this is by C, and M is the bending moment at the point at which you want to compute the sigma. Okay. Now you can see in this figure that this force that is causing the bending moment and the neutral axis, they are both perpendicular to each other. Okay. So whenever you are given a force, or maybe it a UDL, UVL or point load, anything, the direction of force and the neutral axis that you have to choose, about which you will find the I, means moment of inertia. The moment of inertia is found about the neutral axis, and neutral axis is chosen in a way that the force is acting perpendicularly to it. Okay. So if the UDL is acting, so UDL will be here, UVL will be here, or point load will be here, and this is the neutral axis perpendicular to it. Okay. So this is the way of choosing the axis. Okay. So now section modulus or flexural strength. So section modulus Z is equal to I by. I is the moment of inertia, by is the distance of the fiber from the neutral axis. Okay. So it represents the strength of that section or the beam. Now moment of resistance. So moment of resistance is the maximum bending moment that can be resisted by any section without failure. So moment of resistance is equal to sigma P into Z. Sigma P is the permissible stress and Z is the section modulus. So for tension, moment of resistance in tension is equal to sigma PT, which is the permissible stress in tension, into ZT. ZT is the section modulus for tension. Similarly, MRC is equal to sigma PC. Sigma PC is a permissible stress for compression, and ZC is the section modulus for compression. Okay. So ZC will depend upon by C and ZT will depend upon by T. So I will be same, but due to change in by C and by T, ZC and ZT will change. Okay. And sigma PC and sigma PT will be different for different materials. Okay. Both will be different. The permissible stress in tension and permissible stress in compression will be different. Now one another question. So this is the a square or rectangular cross section, and this is the UDL is acting. So UDL is acting, and this is the neutral axis chosen. Okay, so this is perpendicular to it. Similarly, as the previous figure, you can see that this is the neutral axis that has been chosen. Okay, and P is the axial force that is acting and creating a axial tension. Okay, so UDL is giving a bending moment M, and P is the axial tension caused by it. Okay, caused by P. So combined stress sigma is equal to bending stress plus axial stress. So bending stress may be positive or negative depending upon the top or bottom fiber that you are choosing. So in the top you will face tension, and in the bottom you will face compression. So sigma C will be in the bottom and sigma T will be in the top. So based on that sigma value you will have plus or minus sign. So plus for tension and minus for compression. So sigma B will have a sign according to the tension and compression, and this P is the tension. As you can see, this is no compression, this is tension, so this is a positive value sigma A. Now in the second question, this P has been moved a bit, means eccentricity has been given. So it's moved from the midway, it's moved from the mid point. E is the distance that has been moved from the center. Okay, so P is acting now away from the center at a distance E. So this is the P force acting. So this can be made into this diagram, that P has been put in the mid portion, and along with the moment that has been induced by the eccentricity. So this is the bending moment induced due to P. So finally we have combined stress is equal to bending stress plus a stress due to P into E. Okay, and this is the tension force P by A. Okay, axial stress of tension. So at any section you can find the M, means the bending moment. So at any section, if it is asked, you can find the bending moment, and then from the bending moment you can find the bending stress. Okay, wherever you can find the bending stress depending upon the bi value. So whether it's a top or bottom, you can find the sigma value based on that. Okay, now force on any area of cross section. So F is the force on any area of cross section that can be found using this formula, that F is equal to sigma max by max into A into bi bar. So A is the area of that section, bi bar is the distance of the centroid of that section from the neutral axis, sigma max is the maximum stress, and bi max is the maximum distance of the fiber, means the topmost portion or the bottommost portion, whatever it is, it should be the bi max. Okay, now beam of uniform strength. Okay, so in the beam of uniform strength you will have the same bending stress everywhere. Okay, same bending stress everywhere means bending stress is constant. So moment of resistance at a distance x is equal to moment of resistance at a distance L. So this is the beam of uniform strength. So moment of resistance at a distance x is equal to moment of resistance at a distance L. So sigma into zx, because sigma is constant, so sigma into zx is equal to MRL. Now zx is equal to bx into d square for a rectangular cross section. Suppose this is a rectangular cross section. So bx by d square by 6 for a constant depth rectangular cross section, and b into dx square by 6 for a constant depth cross section. Okay, the depth is constant, the width is constant, hence b is there, and x is, and d is varying here. In the constant width the d is varying, and in the constant depth b is varying. Okay, so bx d square by 6 and b dx square by 6. Okay, it's a rectangular cross section, and this is the zx value. So uniform beam of uniform strength mrx is equal to mrl, means sigma zx is equal to mrl, and this mrl is the maximum bending moment along the length. So for a cantilever beam it's W into L, means W is the load acting at the free end, and L is the length of the cantilever beam. So WL will be the maximum bending moment at the fixed end. Okay, so W is the load acting at the free end and L is the length of the cantilever. So W into L is the maximum bending moment along the length of the cantilever. And similarly, for a simply supported beam in which the load is acting at the midpoint, okay, the load is acting at the midpoint, then for this kind of beam the maximum bending moment will be WL by 4. Okay, so you can put this MRL value here and you can find the sigma value according to the ZX. At any point X you can find the sigma value. Okay, so thank you.